Completing organic reactions can be a little tricky. Depending on the type of reaction, there's specific rules or a method that you need to follow in order to predict the correct products. So what we're going to do is go through each reaction individually, and I'll give you an example of predicting the products using these rules or guidelines. So our first reaction is called an addition reaction. Remember, they occur when a double or a triple bond between two carbons is broken and two atoms are attached to your organic compound. Now they're always attached to adjacent carbons, one on either side of where the double or triple bond used to be. Usually this is a pretty straightforward process, but there is a complication. If both of the reactants are asymmetrical around the bond that's being broken, then two isomers are made as products. Our example here is propane doing an addition reaction with water. Let's first draw the reactants. So propane's got 3 carbons, and I've got a double bond between carbon 1 and carbon 2. We usually represent water in organic reactions like this, because what happens in this addition reaction is this bond will break and we'll stick the H on one carbon and the hydroxyl on the other carbon. Notice that around the bond that's being broken, it's asymmetrical. The left doesn't look like the right. Also, that can be said with the propane. If I break that double bond, the left side of the molecule doesn't look like the right side. So here I have 2 asymmetrical reactants, and I'm going to make 2 products. I make 2 products because there's 2 options of where this hydrogen can go. It can either go on carbon 1 or carbon 2. Well, which one is it? Actually, in real life, it gets added to both, and you end up with a mixture of products. So we're going to show both in this case. The first option is to put the hydrogen on the first carbon. I'll indicate that by making that hydrogen red. That hydrogen came from the water. The hydroxyl goes on the second carbon. If I name this molecule, it's going to be propane 2-ol. The other isomer that gets made is just the reverse, where I stick the hydrogen on carbon 2 and the hydroxyl group gets put on carbon 1. In this case, I would get propane 1-ol. So how much of each do you make? Even though there's only 2 options, propane 1-ol and propane 2-ol, they're not made in a 50-50 split amount. We can use something called Markovnikov's rule to qualitatively figure out which isomer we're going to make more of. Markovnikov noticed that the functional group, or the most important or exciting group that's being added on to your organic, has a tendency to go on to what's called the more substituted carbon. This is the carbon that is bonded to less H's. Remember, CH bonds are boring, so if a carbon has less H's, then it's actually considered more exciting or more reactive. So in this case, if we look at where the hydroxyl group is attached, here it's attached to a carbon that only has one H attached to it. On the propane 1-ol, the hydroxyl is a carbon that's attached to 2 H's. That's more boring. So the hydroxyl group is more likely to attach in the number 2 position. Now this is just a qualitative measure. We know we're going to make more propane 2-ol than we are the propane 1-ol, but we don't know how much more. Is it a 60-40 split? Is it a 90-10 split? Markovnikov can't tell us that. All it tells us is we're going to make more propane 2-ol, so we're going to call that the major product. And the propane 1-ol we're going to call the minor product. In order to figure out the percentage, you would actually have to do the experiment, separate your two isomers, and then find their concentrations that you made and do a percent yield calculation. We're not going to worry about that. We're just going to figure out, hey, we've got two isomer products here because we have got two asymmetrical reactants. We're going to name them, and we're going to use Makarnikov's rule to figure out which one's the major and which one's the minor. The opposite reaction is called an elimination reaction. Remember, this is where we have two atoms that are removed from an organic from adjacent carbons next to each other, and we're going to form a double or a triple C to C bond. We also have the situation where we have the complication of making two isomer products when our organic is asymmetrical to start with. We can also use Makarnikov's rule to figure out which one is the major and the minor product. Here's an example with elimination of 2-chlorobutane. So here's my 2-chlorobutane. As we discussed, the functional group, the Cl, is going to be the most reactive part of the molecule. So if anything's going to come off this organic, the Cl is going to be the first thing. In order to form a C to C double bond, I either need to pull off an H off of this carbon or an H off of this carbon. Actually, in real life, both can happen. I recognize that I'm going to get two isomers because this organic is asymmetrical around the first functional group I'm going to pull off. Notice I've got a CH3 on this side and I don't have a CH3 on this side. So I'm going to draw both possibilities. So the first one is I'm going to pull an H off the first carbon, so that becomes a CH2, and I'm going to form my double bond in between carbon 1 and carbon 2. So I would call this but1-ene. The other option is to pull off this chlorine and then pull an H off of carbon number 3 and form the double bond in the second position. That would give me the product but2-ene. Now I'm going to make a mixture of these two products, but I'm not going to make them in a 50-50 split. We can use Makarnikov's rule to figure out which one I'm going to make more of. Makarnikov says that the more substituted carbon next to the functional group usually loses the H. So if we go back here and look at our functional group, here we have a carbon that's got 3 H's attached to it, and over here we've got a carbon that has 2 H's attached to it. Remember, if you have less H's, your carbon is more reactive. So this carbon here is going to be more substituted, and most of the time we're going to get the double bond formed in the second position. We can then label our but2-ene as the major product, and our minor product is going to be the but1-ene. Now, if you're doing additions or eliminations and you have your reactants symmetrical around the bond or the functional group, then you only ever get one product. So you have to be aware when you're completing these types of reactions, are my reactants symmetrical or asymmetrical? The third type of reaction is called a substitution, and there's no real special rules here. What you do is you pull off a hydrogen or a functional group and you just replace it with a different functional group. The only kind of guideline is that you can only break one bond in order to do the substitution. It's not like you're going to be making an ester and chopping out, breaking this bond and taking the ester and getting rid of it. That just doesn't happen. It's too much work. Whenever we do organic reactions, we typically only break one bond. Here's an example of a substitution that works. If I have a benzene and I react it with hydrochloric acid, I'll just show the line diagram of the benzene here. Remember, each carbon has 1.5 bonds in the ring. That means they each have one hydrogen attached as well. Now, substitutions are the only reactions that aromatics tend to do because the 1.5 bond system in the ring is really stable. What I'm going to do is remove this hydrogen, and when I react it with hydrochloric acid, this bond between the H and the Cl also gets broken. And what's going to happen is the exciting functional group in the hydrochloric acid, so the chlorine, is going to take this hydrogen's place on the benzene. Now I am going to make a second product here, and I've got two H atoms, so they're just going to bond together and make hydrogen gas. The name of my organic is going to be 1-chlorobenzene. What I want you to do is pause the video here and go to the worksheet. Try out question number 2, where I give you the reactants and ask you to predict and name the products and identify what type of reaction it is. If you do parts A to F, they are either going to be additions, eliminations, or substitutions. Take 15 to 20 minutes to work on these questions and check your answers as you go. When you finish this, unpause this video and we'll do the rest of the reactions. Okay, let's carry on and talk about oxidation reactions. Oxidation and reduction reactions are exact opposites, like we've previously discussed. In oxidation reactions, your organic always forms more CO bonds, or if you want to count CH bonds, there's always less in your products after an oxidation reaction. You're going to recognize an oxidation reaction because there's going to be a plus square brackets O, which stands for an oxidizing agent. There's many oxidizing agents we can use, depending on how many times we want to oxidize our organic. An example is acidified potassium permanganate. There's a particular way to add CO bonds to an organic. First of all, your oxidizing agent is going to attack any hydroxyl groups, any C single bonded OHs, and actually steal a hydrogen from the oxygen and from the carbon so that a C double bonded O can form. If your organic doesn't have any OH groups, then the oxidizing agent will pull off an H off of a carbon and replace it with a hydroxyl functional group. Here's an example where we're going to actually double oxidize ethanol. We know we're going to oxidize it twice because there's this 2 out in front of the oxidizing agent. And I'll show you this step by step. So with the first oxidizing agent, it's going to attack this OH group and change it into a double bond. So that changes my alcohol into an aldehyde. If you continue to oxidize this aldehyde, you notice that there's no more hydroxyl functional groups. So what this oxidizing agent is going to do is it's going to remove this H right here. Why this H instead of one of these? Remember, the functional group on your molecule is always the most reactive. So the reaction is always going to happen on this carbon, not this one. So this oxidizing agent is going to remove that final H on my second carbon, and to increase the CO bonds, it has to replace it with an OH. Now I've done a double oxidation. Notice in my reactant I only have one CO bond. In my final product I've got three. I've got this double and the single. Now I don't mind on quizzes or tests or in your practice if you don't show this middle step. If you want to go straight from this alcohol down to this carboxylic acid, that's absolutely no problem. I'm going to name my product here. I've got two carbons, a single bond between it, and I've got a carboxyl functional group, so I'm going to use oic acid as my suffix. For reduction reactions, my product is going to have less CO bonds or more CH bonds than my original reactants. Again, you're going to recognize this because you're going to have a plus H in square brackets. That doesn't necessarily mean we're adding hydrogen. It means it's code for a reducing agent. Although we can add hydrogen gas as one of these reducing agents, but there's many different kinds. There's a particular order for removing CO bonds. You start by substituting any hydroxyl groups with just a single H. Hydroxyl groups are easier for the reducing agent to break off and replace as opposed to trying to attack a C double bonded O. But if your organic doesn't have any hydroxyl groups, then you change any C double bonded O's into singles. Here we have an example of pentanal being reduced. So I have 5 carbons, single bonds between them, and I have a carbonyl functional group on this end carbon. If you're looking at this molecule, there are no OH groups. So I have to go and attack this double bonded O and change it into an OH. Now this reducing agent is going to supply the oxygen with a hydrogen and this carbon with a hydrogen so that they remain stable with the required bonds that they need. This gives me my product pent and 1-ol. And if you reduce an aldehyde once, you end up with an alcohol. Our next pattern is called a condensation reaction. We're going to take 2 organic molecules and join them together and having water as a second product. That's why it's called a condensation. Now don't get misled. Every time you make water as a product does not mean that you have a condensation reaction. You always focus on, hey, I've got 2 organics and now they're linked together. There are 3 common patterns for condensation. You can link an alcohol and an alcohol together to make an ether, a carboxylic acid and an alcohol to make an ester, or a carboxylic acid and an amine to make an amide. Here's an example of making an ester. If we have but-2-inoic acid, and react it with propane 1-ol, we're going to make this ester here. Now, as a little trick, you've noticed I've drawn the organics so that the functional groups are facing each other. It's going to be easier for you to see what's going on. Each of these organics, remember the most reactive part is the functional group, so it's the functional groups that are going to react together, not the opposite ends of the parent chains. Remember in this definition of our condensation, we're going to link these two organics together and we're going to make water as our second product. Do you guys see where the water comes out? I'm going to take the hydroxyl group off of one organic and the H of the hydroxyl group off the other. Now, to be honest, it doesn't matter which one I take if I've got a carboxylic acid and an alcohol. I end up with the exact same result. So this is going to come out as my second product, water. And this carbon now, it only has 3 bonds, so it's going to look for something to bond with. This oxygen only has 1 bond, so it also needs to bond with something else. If there's nothing else in the container, those two atoms are going to bond to each other. And here I have my ester. See the cocoa? Remember when you're naming esters, the piece with the double bonded O automatically becomes your parent. And they're the weird ones, right? Whatever's attached to the other side of the O, we put in front of the name, and we leave a space. Hydrolysis reactions are the exact opposite, where we have a large organic and we split it into 2 smaller organics using water as our second reactant. Now it's important to know that you can only break CO bonds and CN bonds in a hydrolysis. Never, ever, ever a C to C bond. The other important thing to highlight is when you're breaking your organic apart, you need 2 organics made. There are 3 common patterns, and they're exactly the opposite as the condensation patterns. If you take an ether and react it with alcohol, you'll get your 2 alcohols back. If you take an ester reacted with water, you're going to get a carboxylic acid and an alcohol. And if you react an amide with water, you're going to get a carboxylic acid and an amine as your products. Here's an example. So if I have N-butyl ethanamide, and I react with this with some water. Again, we represent water as an H bond OH. What's going to happen is the water is going to be broken apart. And the H is going to go on one molecule, and the OH is going to go on the other. Now, it's important to know that when you're hydrolyzing an amide, it's always this bond right here that gets broken to create your two organics. This C right here just lost a really important functional group, so it's going to fight like heck and steal this hydroxyl group and become a carboxylic acid. This nitrogen, it's okay, it already has an important functional group on this side of the molecule, so it's okay taking the other hydrogen from the water. My first product is going to be ethanoic acid. If I stick the hydroxyl group on the piece with the double bonded O. And my second product is going to be butane 1-amine. So here I've taken an amide and I've gotten my carboxylic acid and my amine back. On the bottom of your note is a little graphic organizer that shows you how the 7 organic reactions can change one family into any of the others. That's the great thing about organic reactions. If, for example, I need an aldehyde that I'm not allowed to buy for safety reasons, or it's really expensive, I could actually simply make it from an alcohol I can buy that's cheaper and doing an oxidation reaction. You could change any organic family into any other ones. Now this is just an intro concept organizer. They are missing a couple of families on here. Remember, if you take a carboxylic acid and an amine, which isn't on this chart, you could make an amide. So they forgot a couple of branches on here. So it's a good start. Now that we've covered the rest of the reactions, you can complete the rest of your worksheet. If you've done question number 2, A to F, remember these are all the addition, elimination, and substitution questions. G to N are your oxidation, your reduction, and your condensation and hydrolysis questions. Also try out question number 3. Given a specific molecule, can you show different reactions that it can actually perform? Now there's more than 3 possible ones for hep 1-ene 4-ol, but I'm just asking for 3, so pick your favorite.